Hello students, we are going to study atomic spectra, evidence for the quantized electronic energy levels. Okay, and topics we will be covering: spectrum, atomic spectrum, okay, absorption spectrum, spectrum of hydrogen. We will be starting right now with spectrum. What is spectrum? Actually, when ordinary white light passes through a prism, okay, it disperses into 7 different colors having different wavelengths, okay, and this is arranged one after another, okay, in a band, and this is known as what? Spectrum. Okay, I'll make you understand. Suppose you have taken a prism and you are passing a what? White ray of light. Okay, now what happens in this? It gets refracted, okay, and then okay, here it spreads out into 7 okay different colors, splits into 7 different colors. 2, 3. And these 7 different colors also, you can see what? The deviation is in a different manner. Why? Because of the different wavelength. Red has got the largest wavelength, so it will be deviated the least. Okay? And violet has got the least wavelength, so it will be deviated more. Okay? And this here you can see, when this all 7 colors, okay, with gear, okay, these 7 colors, okay, when it is arranged in a band, here you can see this is known as what? Spectrum. Okay. Now, when we are talking about this spectrum, what we are saying? Here, red is here, okay, orange, yellow, they are in a continuous manner, okay. Here, if I say, suppose this, I am arranging it in this manner, okay. Here, you can see all this color, okay, this red, here it is what? After that ends also not, you will see that what the color orange starts. It seems that this both colors are merged, okay, and then yellow, orange and yellow, you can't make out the difference or make out the boundary, okay, because they are continuous in nature, and so this is known as, this type of spectrum is known as a continuous spectrum. Okay. Now, next we are going to study emission spectrum. So, what is emission spectrum? First, I must explain you that. Suppose you have taken any element, okay, and you have provided energy to it. Okay, when energy is provided to it, what happens? The atom gets excited, but it has to come in its own place. While it is coming to its own place, what happens? It emits what? Electromagnetic radiations. And these electromagnetic radiations are of different wavelength. Okay, so here we can see the spectra of radiation emitted by a substance has absorbed energy and is called what? Emission spectrum. It has taken the energy, okay, it has what? Been excited by taking it, absorbing the energy and taking and getting excited, and when it comes back, it emits this in the form of what? Electromagnetic radiations, okay, and then it is known as what? Emission spectrum. This emission spectrum is studied by what? Spectroscopy. Okay. Now, next, they emit light only at specific wavelength with dark spaces between them. Here emitted radiations is identified by the bright lines, so it is known as line spectrum. So here now this emission spectrum is also known as line spectrum. Why it is known as line spectrum? Because it is emitting light only of specific wavelength. Okay, and as a result there will be dark spaces and you will be observing bright lines, and this is why it is known as what? Line emission spectrum. Okay, next, radiations in the spectrum are emitted due to the energy changes in the atom, and so it is known as atomic spectrum. Here you can see what? When the radiations are emitted, it is of different wavelength, having different energy, and as the result it is representing that atom only, and so it is known as what? Atomic spectrum. Okay, now suppose if you have taken a sample of hydrogen over here, okay, we are now going to study experimentally what? Emission spectrum. Okay, and you have provided energy to it. Okay, as the result what will happen? It will be excited, isn't it? And so here this excited sample has been kept. Okay, but I said to you it will come to its own position. As the result it will emit radiations. Okay, so what happens? Here we have used a slit, okay, in order to concentrate the radiations in one direction. Okay, it passes through the prism, and you can see over here there is a detector, okay, or you can say a film. What happens here, after passing through the prism, as it is having different wavelengths, you will be seeing there will be a number of what? Bright lines and dark lines. Okay, and one thing you have to remember is that the presentation of the bright lines and dark lines are specific for a particular element. Okay, and it will be always the same whenever we do it, whenever we do the experiment of emission spectra. So now absorption spectra. Okay, absorption spectra is just, I'll say, opposite of emission spectra. Emission, it is emitting; absorption, it is absorbing the radiation. Okay, so here when white light is passed through a solution or vapors of a chemical substance, okay, here we have taken what? Hydrogen. It absorbs the light of certain characteristic wavelength, and the other wavelength is transmitted. It means what? It is absorbing the light of certain wavelength and the rest it is transmitting. Okay, and this produces a series of dark line on white background because some of them are absorbed and some of them are transmitted. As the result, what happened? A white background is created on which we can see the dark lines. Okay, now here there is a difference from the emission spectrum, isn't it? Because you have taken this absorption sample over here, isn't it, in the solution of vector form. Okay, and here you can see it is being absorbed. Okay, and other wavelength is being what? Here it is being absorbed and other wavelength is being transmitted, isn't it? And which is being transmitted, okay, you will be seeing over here in the absorption spectrum. Here in emission spectrum, if it was what? Bright color or bright lines, you will see in absorption dark. Okay, because why? Absorption spectrum is just the opposite of emission spectrum. Here we have taken same sample, that is of hydrogen. Okay, so whatever we are getting in the spectrum, you will be seeing it will be just opposite to the emission spectrum. Okay, so now the line spectra of hydrogen. Okay, we are going to study. what happens in the case of this hydrogen? Suppose the electron is present in this ground state, okay? When we are providing energy, it moves to what? A different higher level, isn't it? And now, after that what happens? It tries to come back to its own position. It will radiate energy. So if it falls in this place, in its original position, it is what? It is known as Lyman. It is known as what? Lyman series. Okay. Now, if it falls in this second, it is known as Balmer series. Okay, and if in the third, it is known as Pascal series. Next, bracket series. If it falls on the fourth, okay, and the last, fund series. Okay, if in fifth. So, if in the fifth one. Okay, so here you can see Lyman N1 will be what? Okay, it means where it is falling. Okay, where it is coming. N1 will be 1. You have seen over here. Balmer series, it will be 2. Pastel series 3. Bracket series 4. And fund series 5. Okay, but yes, it can also be 2, 3, 4 and 5 and all. Okay, so N2, the final one. Okay, we can be taking what? 2, 3, 4 or 5. For here, it is 2 only. So it will start from what? 3, 4, 5. Okay, in Pascal series, it is 3 only. So it can't go below that. It will be becoming more than that only. So 4, 5, 6. Okay, bracket also like that only. It will be 5, 6, 7 and 2. And fund, you will be seeing it will be 6, 7, 8 and so on. So this Lyman series, okay, what is its spectral region where it is present? It is in the ultraviolet region. Balmer series in the visible region it falls. Okay, Pascal series in the infrared region, bracket series in the infrared region, and fund series in the infrared region. Okay, now for the calculation or doing the numerical, okay, first Balmer has given with the visible region only, okay, but later on this Rydberg came and he gave the calculation of wave number which we are using in the numericals. It is that what wave number or wave number will be represented by what? 1 upon lambda, okay, so that is equal to what? Rydberg's constant in the bracket 1 upon n1 square, okay, minus 1 upon n2 square, okay. Now for here I will explain you also a bit more. Here you can see I have written n1 square and 2 square. Suppose if in the numerical it comes what? The initial and the final positions. You will be taking the values over here only n1 square and n2 square in this region. Okay. Now for hydrogen like particles, here hydrogen is having only one electron, so no need to take the atomic number. But like that, hydrogen like particles like helium, lithium and all, okay, like from lithium if you take out 2 electrons it become alive 2 plus, isn't it? So here like that, how will you calculate? Wave number is equal to Rydberg constant in the bracket 1 upon n1 square minus 1 upon n2 square, and here you have to write the atomic number of that element, okay, because Z represents what? The atomic number, okay, of that element. Okay, this is all for today. Good day, take care.